Hi, today we are looking at circular motion occurring vertically. So with this, we'll have to take into account gravity. So we'll start talking about some of the basics of it. So with centripetal force, it is the net force acting towards the center of our circle. As we've talked about before in previous notes, it can be caused by tension forces, friction forces, forces of gravity. It can be a combination of those forces. Now, if our centripetal force is a net force acting towards the center of the circle, then the force of tension keeping an object moving in a circle will vary depending on where the object is in the vertical circle. So I've drawn out a diagram. So I have a circle and I've drawn out 4 different points where we have velocity, weight, and tension. So we can see that our velocity is creating a tangent to our circle at each of those points. And we will have tension forces acting towards the center. Now at the top of our circle, force of gravity is acting towards the center of the circle, so we wouldn't need as much of a tension force. Where we can see at the bottom of the circle, force of gravity would be acting away from the center of the circle, so we need a stronger tension force than we would at the top. At the sides, our tension force would be equal whether it's on the left side or right side. So due to these changes in our forces, depending on where in the circle our object is, we will often get questions about the minimum speed at the top of the circle, so if our circular motion continues. For these questions, our tension force at the top of the circle will equal 0. This leaves only our gravitational force to create a centripetal force. So for example, a roller coaster goes through a vertical loop of radius 25 meters. What is the minimum velocity that the coaster has to have to make the loop? So we have radius is 25 meters. We're looking for our velocity. Now, like I mentioned, at our minimum velocity at the top of our loop, our force centripetal will be purely caused by our force of gravity. So we can say our force centripetal is equal to our force of gravity. Now we know force centripetal is mass times our speed squared divided by r. And we know our force of gravity is a mass times gravity. So we can substitute those into that first equation. Now you'll find that we have mass on both sides of our equation, so that cancels out. We then want to start rearranging to get our speed or magnitude of our velocity on its own. So I'd multiply both sides by r, and then to get rid of the squared, take the square root of both sides. At this point, substitute our values in, and we find that the minimum velocity for the coaster at the top of the loop would be 16 meters per second. Next example, a string has a breaking point of 150 newtons. If a 3 kilogram mass is attached and swung in a vertical circle of radius 1 meter, what is the maximum speed at which object can move at without breaking the string? So as we talked about a couple slides ago, our tension force at the bottom of the loop is going to be much greater than at the top of the loop, because at the bottom of the loop it has to create the force centripetal as well as overcome the force of gravity. So if we look at the bottom of the loop, we'd have essentially a tension force going up while we have a force of gravity going down. So we are going to calculate a tension force using a tension force of 150 newtons, because that's going to be our maximum amount that we can have before it breaks. We're given our mass is 3 kilograms and a radius of 1 meter. Now from our diagram, we can see our force centripetal, which is essentially our net force towards our, or away from our center, is equal to the force of tension minus the force of gravity. Now, our force centripetal we know as our mass times our speed squared over our radius, while our force of gravity is mass times gravity. Now we'll start rearranging this to get the speed on its own. Now, unlike the previous example, we can't cancel out our mass because it's not involved in our force tension, so instead we'll divide both sides by it. Then we'll multiply both sides by our radius. And lastly, we'll take the square root of both sides, substitute our values in, and we find that we get a speed of 6.3 meters per second. So any quicker than that, and the string would break. Okay, next example, we have a 2.5 kilogram object being swung at the end of a 0.75 meter string at a speed of 7.5 meters per second. We only know what the minimum and maximum tensions in the string are. So essentially, we have our mass, we have our radius, we have our speed, and we only find the maximum tension and minimum tension. Now I've decided to solve for the maximum tension, which would be at the bottom of our loop. Now at the bottom of our loop, our tension has to be enough to overcome the force of gravity and supply the force centripetal. So therefore, our tension max would be our force centripetal plus our force of gravity. Now we can substitute in equations for each of those. So our maximum tension is equal to mass times our speed squared divided by our radius plus our mass times gravity. Substitute our values in, and we find that we have a maximum tension force of 210 newtons. The minimum occurs at the top. At the top, our centripetal force is being caused by both our force of tension and our force of gravity. So if we take our force centripetal and subtract our force of gravity, that gives what remaining force our tension must provide. And once again, substitute our values or equations in, substitute values in, and we get that at the top of a swing, or top of a loop, we have a tension force of 160 newtons. Next example, we have a 1,800 kilogram van going over a hill with a radius of 75 meters at 20 meters per second. We already know what force normal does the road exert on the van. So I've drawn this out so we have this van, which I've drawn in our force normal and force of gravity acting on it. I've also drawn in our radius and our speed. Now we know our mass is 1,800 kilograms, our radius is 75 meters. We have a speed of 20 meters per second, and we're looking for force normal. Now in this case, if we look at our forces acting towards the center of our circle, we can figure out our force centripetal, which is essentially our net force acting towards the center. So we have a force of gravity acting towards the center, but we have our force normal acting in a different direction. So therefore, I can say my force centripetal is my force of gravity minus my force normal. I'll move force normal to the other side of the equation, move the force centripetal to the other side, fill in our equations of mass times gravity and mass times speed squared over our radius, and fill in our values, and we get that the van has a force normal of 8,100 newtons.